In this video, I want to talk a little more about arc length, but this time I want to turn my parametric equations, my vector functions, into ones that are parameterized by arc length rather than time. And we'll see why over the next couple of videos. But here's what I usually have, right? I usually have a curve in space or in the plane, whatever, which is defined in term by some vector function. Okay, and at t0 you might be right here, at t1 you might be right there, and at t2 you might be there, and t equals 3 here, and t equals 4 there. And depending on the parameterization, you aren't necessarily moving at constant speed, right? And so to say something like, well, after 5 seconds, how far have you moved from time 0 to time 5? How far have you moved along the curve? Well, that's going to take some calculating, right? You're going to have to do that arc length integral that we did in the previous video, the integral from 0 to 5 of the square root of the integral of the length of the speed, right? The integral of the length of the derivative function. Well, what if instead of time, what if my parameter was distance moved along the curve? So the question of how far have you moved from t equals 0 to t equals 5 would be something like, well, how far have you moved after you've gone 5 miles down the road, right? I mean, think about the highways generally have mile markers along them, right? And so at mile 0, you're right here. That's mile equals 0, and this is mile equals 1, and mile equals 2, and so on. And I could say, well, if you started at mile 0, when you get to the 3-mile marker, how far have you gone? Well, the mile markers are actually measuring the miles that you've gone. So when you get to the 3-mile marker, you've gone 3 miles. Assuming you started at 0. Okay? And so if I can parameterize a curve by arc length, so I've got some curve and I say, well, this is my starting point, and when I pick a measurement, am I measuring in feet and inches and miles and angstroms? What am I doing? But if I go 1 unit of distance, so that would be s equals 1, and then I go 2 units of distance, that would be s equals 2, and here 3, s equals 3, and each arc length from here to there, from there to there, from there to there are all the same because we're measuring by arc length. Right? So 1 unit increment is always the same as 1 unit increment of arc length. So the question is, how do we get to parameterization in terms of arc length? So let's do an example here. This is one of my favorite examples for curves. I'm going to let r of t equal cos t sine t t. So this is the standard helix, radius 1, going up at a rate of z equals t. Now, we saw in the previous video that the length of the derivative vector was the square root of 2, right? Which meant I wasn't moving at unit speed, I was moving faster than that. So what I want to do is if I were to calculate arc length, right, from, let's say arc length is the integral from 0 to whatever time I want to stop at. Well, how far have I moved along the curve from t equals 0 to t equals, well, let's say t here, okay? Then this would be the length of r prime of, I'm going to use a dummy variable here because I want the t to be in the thing there. Take the derivative of r, take the derivative of r, take the length of that, integrate it, and then plug a t in and plug a 0 in and subtract. And then you will have the arc length as a function of t, right? So whatever my curve looks like, here's t equals 0, here's t equals t, and what I'm calculating with this integral is that length right there. So that length s will be a function of t, the stopping point t. So in this case right here, right, for this one, r prime of t is minus sine t cos t1. And if I do the integral, sorry about all the beeping in the background. I don't know if you can hear it, but I seem to be on a group chat that everyone seems to want to talk at the moment. Let's go. The arc length is the integral from 0 to t of the square root of sine squared t plus cos squared t plus 1, which dt, no, dq, right? I'm doing a dummy variable in there because my variable is t right there. Anyway, sine squared q plus cosine squared q is still 1, add 1 is 2, so I've got the integral from 0 to t of the square root of 2 dq, which would be the square root of 2q evaluated between 0 and t, which is the square root of 2 times t minus the square root of 2 times 0. Right? So the arc length is always square root of 2 times t, which means that t is s divided by the square root of 2. Then if I take that and plug it back in for t, I can say that r now as a function of s is the cosine of s divided by the square root of 2, comma, sine s divided by the square root of 2, comma, s divided by the square root of 2. So what I've done is I've reparametrized this curve. Instead of using t as my parameter, I'm now using s as my parameter. Now, just to double check and show you that this works, if I now look at the derivative r with respect to s, and I'll write this out this way because here when I said r prime, it was with respect to t. If I say r prime now, does that mean it's with respect to t or s? I'll just be clear. I'm taking the derivative with respect to s. So if I take the derivative of this with respect to s, I get, well, there's a chain rule that happens here. So this would be, there's a minus sine s over the square root of 2, but then take the derivative on the inside, which would be 1 over the square root of 2. Likewise here, I've got the cosine of s over the square root of 2 times 1 over the square root of 2. And then this one, the derivative is just 1 over the square root of 2. And notice now that when I take the length of this would be 1/2 sine squared s over radical 2 plus 1/2 cosine squared s over radical 2 plus 1/2, and this shouldn't have been that. It should be a square root. I'm taking the square root of all that because I'm taking the length of the vector. And factor the half out of that thing. Sine squared plus cosine squared is 1. So I'm left with the square root of 1/2 plus 1/2, which is the square root of 1, which is 1. By reparametrizing, I went from having a speed that was always radical 2 to a speed that's always radical 1. Okay. Now, the process of reparametrizing with respect to arc length is the same every time here. You are doing the integral of, let's back up a little bit here. You're doing the integral of the length of the derivative vector from 0 to t, right? This is not always an easy integral to do, but once you do it, you'll have s as a function of t. You then need to solve that equation, right? We had s as a function of t. You now need to solve that equation for t, so that I have t as a function of s. Then I can plug those t's back into my parameterization, back into this thing up here, and now rather than being a function of t, I would have it as a function of s. Okay. If you are parameterized by arc length, then you always have unit speed, and increments in the parameter is the same things as increments in arc length along the curve. How far along the curve have you gone when you've traveled 5 miles? Well, you've gone 5 miles, right? That's parameterizing by arc length makes it really easy to say how far you've traveled based on how the parameter has changed, because it's the same. Anyway, there you go, parametrizing by